So just to review real quick, we had this example of a traffic light controller, and the purpose of this was to control the traffic light at an intersection. Sorry. And we have these two states where Academic Boulevard is green and Bravado Boulevard is red. That's one state. And then the other state is when they're flipped. You know, the Academic is red, Bravado is green. And then there's two additional states that are for the yellow light for each street. And so we transition, whenever we go from green to red, we go through this transitionary state for one cycle. And in this case, one cycle, the period of the clock is assumed to be the length of time that the light is yellow, right? So obviously, if we were running this at 200 megahertz or gigahertz, you know, this wouldn't make sense in that case, because as we pass through this yellow light state, it would only be in there for one cycle, and you wouldn't see it actually turn yellow because it would be too fast. You guys with me on that? Does that make sense? Okay. So the one thing that it might be a little unclear with these is that there is some shorthand involved in this notation. Notice that these arcs have transitions, but in some cases, even though there are two inputs to this system, TA and TB, only TA is shown here, right? So it's like, where's TB? Why isn't it here? Well, it's just assumed to be a don't care, right? We don't care what TB is because we're waiting for the traffic to let up on Academic. That's the whole point of this transition. And so we don't care what TB is. So when you construct your truth table for the next state logic, you have to be aware that TB is a don't care, right? Everyone with me? Make sense? Okay. Now the other thing you'll notice is that LA and LB are the outputs, and they're listed inside the states, and this is because this is a Moore machine. Moore machines drive their outputs according to whatever state the system is in, and so you can't change the outputs until you change state, right? Which is going to happen in the next cycle at the earliest. Everyone with me? Right? Okay. Oh, also notice that there's these loopback states that are shown here, where you would stay in this state across multiple clock cycles as long as this TA is true. As long as you still have traffic at Academic, we're going to keep the light green. Okay? Okay. So from the state diagram, you can construct the next state table. And initially, you can just give the states symbolic names like S0, S1, S2, S3. But eventually, you have to choose encodings for them, which is arbitrary. You just have to make sure that you give each state a unique binary value. The minimal number of bits for the states is going to be the log base 2 of the number of states rounded up. So there's 4 states, so log base 2 is 2. So there's 2 bits that make up the state encodings. And then once you have the state encodings, then you can build a truth table. Notice here in the truth table, they actually have a don't care here for the traffic at Bravado when we're in the state where the Academic light is green. And then the output logic is, because this is a Moore machine, we construct the outputs as a function of the inputs. And then once you've got the truth tables, then you can build the logic, the next state logic, the Boolean expressions for the next state logic, and then from that you can design the circuit with gates, and you'll have a complete circuit. When you're debugging this, you would debug this or evaluate this circuit in a simulator that would show sort of a time scale view of what's happening. Usually the clock is at the top along with reset, and the clock just divides the operation into cycles. And then each cycle you can see how you've got transitions in the current state. The current state is only going to transition at most once per cycle. The next state logic is combinational. So if I were to do some, toggle the inputs arbitrarily within a cycle, you might see the next state, which is S prime. That might change multiple times within one clock cycle, but the current state only changes once per clock cycle. Okay, so we talked about encodings, and then as far as the Mealy machines go, this is a variation where you take the outputs and you take them out of the states and you put them on the transitions. And from a circuit point of view, what that involves is just making the output logic a function of the state and the inputs, right? So the authors of the textbooks show that, the author of the textbook shows that by putting the output column in the same table as the next state. You see that? To emphasize the fact that the output has the same inputs as the next state in a Mealy machine. Whereas with the Moore machine, with the traffic light controller, they had a separate table here just for the output logic. Okay. Okay, so that's Mealy and Moore machines, and then you can also break complex state machines into smaller interacting finite state machines. The problem with this is that, as far as I know, there isn't a methodology for doing this. This is kind of arbitrary. But I think the point of this section is that you can do it. In this case, if you add this parade mode, you can make the parade mode its own FSM that sends an intermediate signal into the light's FSM. Why do we do that? Well, it's because the parade mode has to have a state. Whether you're in or out of parade mode requires you to have a state associated with that. Because, and the whole reason for that was, it was kind of contrived, but they said that if you go into parade mode, you just have to assert the parade mode bit, the input bit, for one cycle, and then it'll go into parade mode, at which point you don't have to, the user doesn't have to keep asserting parade mode, in other words, right? So the parade mode controller is the thing that remembers that you're in parade mode. You guys with me? So it's like a toggle. You toggle it on and then it remembers it's there, and thus you have to have state for that. All right, so and then we talked about timing. So I wanted to cover one more example of this. I was going to go through, there's an exercise in the book here that's, I think it's pretty neat. So there's this exercise 3.29. I don't know if you can read that. Let me make this zoom in a little bit here. Okay, so there's this exercise. It says, your company, Detectorama, would like to design an FSM that takes two inputs, A and B, and generates one output, Z. The output in cycle N is either a Boolean AND or of the corresponding input in the previous input, depending on the other input, right? So there's two parts to this. You've got an input A, and the state machine has to remember what A was in the last cycle, right? That's number one. Number two is there's another input called B that controls whether the output is an AND of A and old A, or if it's going to be an OR of A and old A. You guys with me? So there's basically there's two modes. There's I want this thing to be an AND gate or an OR gate, and the OR gate or the AND gate, depending on which ones I select, is going to take the inputs according to the current value of A and the last input of A. You guys with me? It's kind of a little strange, but so basically, if B equals 0, then I want this circuit to be an AND gate between A and old A. When I say old A, I mean the input A as it was in the past one cycle, right? Whereas if B is 1, I want this to be an OR, and this is Z, by the way, the output. Z is the output. A and old A. Right? So the first question it asks is this a Mealy or a Moore machine? Well, it's a Mealy machine. We know it's a Mealy machine because the output Z is it doesn't just depend on the state. It depends on the state, meaning what was A in the last cycle, right? That's the state. The state is basically whatever A was in the last cycle. That's the state. So the output depends on the state. Old A is the state. And it depends on B. So it's a Mealy machine. This cannot be a Moore machine because Z has this, it's kind of the textbook definition of what a Mealy machine is, which is the output is a function of the current input, which is A, and the state, which is old A, right? Okay, so how would we design the finite state machine for this? Well, it turns out there's the state machine, or at least the states themselves are kind of simple. There's only two states in this system. There's one state corresponding to the old A was 1, and there's another state which is the old A was 0. So there's just two states. So this is old A equals 0, old A equals 1. I shouldn't say old. I should say previous A. Not really old, and it's just old in the sense it was one cycle ago. Right? Okay, and then so if I'm in this state and my A is 1 currently, then in the next cycle, I want to go to the state that says my old A was 1, right? Because after I arrive here, presumably A is going to change to a new value, right? Make sense? Likewise, if I'm in this state and my A is 0, then I'm going to go to this state which is, A equals old previous A is 0, right? So you could think of this like, I like this example because it shows that, the state sort of, in this case, you can see the state kind of lags behind the current input, right? That's the idea. It's lagging behind because every time you get a clock edge, it's going to capture the current value and it's going to hold it for a cycle, right? So that's why, that's why I'm looking at what A is now, but on the clock edge, I'm going to register that as the old A because, the A is going to change while I'm in this state, right? That's kind of the idea, right? Okay, so what about B, though? Well, B does not influence the state transition. So B is a don't care with respect to the transitions, to the state transitions, right? But it does matter for the output. But because this is a Mealy machine, the output's on the transitions, not in the states, right? So as a result, I got to stick my output up over on the states here, right? So let's see. So if I'm, let's see. Also, by the way, I've got these loop backs, right? Here, right? Now so if I'm in if I'm in this state, and meaning that my previous A is 0, right? My current A is 0. What does that mean? That means that my output Z is supposed to be if B, let's say if B is 0, that's and, right? So Z is going to be, well, it's going to be 0 and 0, right? Because my old A was 0, my new A is 0, so 0 and 0. On the other hand, and I need a new transition for this, if my A is 0 and my B is 1, that means that my Z is going to be an OR, right? But it's just going to be 0 or 0, which means that my output's still 0, right? Now, if my A is 1, and let's say my B is 0 here, right? That means my Z is going to be but it's going to be 0 and 1, right? Yeah, because my old was 0, my new is 1. But likewise, if my A is 1 and my B is 1, that means my Z is going to be 0 or 1, right? Yeah, 0 or 1 equals 1, right? Right. So notice I'm putting the z on the transition, and also notice that now I have to have multiple transitions, which looks kind of funny, but you have, in a Mealy machine, you have to have the you may have more than one transition from one state to another, because you have to differentiate the different possible outputs, output values. And then over here, I have two options as well. So if my b is 0 versus my b is 1, my b is 0, this would be a and 0. So my z would be, 1 and 0 would be 0. And over here, my z would be, the b is 1, so we're doing OR, and this would be 1 or 0, so 1. Right? And finally, yeah, I've got one more here, right? Loop back, right? And this would be a equals 1, a equals 1. Let's say b equals 0, b equals 1. And this would be z equals, this is an and. So this is 1 and 1 is 1, right? And this is 1 or 1 equals 1 for that. Make sense? Also, oh, by the way, I'm going to, assuming that when I reset this, I'm just going to reset to that state. So when I start up, I'm going to assume that when I start this system up initially, I'm going to assume that I'm going to start in this state. So I'm going to assume that my previous was 0, even though, yeah. I suppose I could add, if I wanted to, I could add my dedicated reset state. Is another option, but I'll just reset on that state. I don't think the problem was specific about how to handle reset, right? Yeah. Make sense? Okay, so so this is not too bad, except my next state table. Well, my next state table actually, I don't really care what b is, right, for my next state table. So I could build my next state table just as a function of the current state. So if this is state 0 and that's state 1, then I could say current state 0, 0, 1, 1, and then I can have a 0, 1, 0, 1, and then I can have next state. Right? In fact, I think that in this case, the next state doesn't even depend on the current state. It's a don't care. Because my next state, if a is 0, I'm going to go to 0. If a is 1, I'm going to go to 1 either way. So it turns out that the next state function is trivial. The next state is literally just a. Right? Now you might say, well, that's pointless. You're going to make a design where you say next state is a. Well, yeah, but keep in mind that it's going through a flip-flop, right? So basically, it's when you do the hardware for this, it's going to look like this. It's going to be like you're going to have a flip-flop with a clock and a reset, right? And then you're going to have a going in, and this is your state, current state. Right? So this is pretty simple. The current state is literally just the delayed version of a. When I say delayed, it's the registered. Sometimes they call this the registered version. It's a through a register or a through a flip-flop. Right? Now the output logic, on the other hand, is going to be a little bit more complicated, because for this, I need 8 rows in my truth table, because I've got 3 possible variables here now. I've got current state, I've got a, and I've got b, and so that's 2 to the 3rd power, right? Rows. So I got to build that. Got to have a, let's see, current state, a, b, z. So current state 0, 0, 0, 0, 1, 1, 1, 1. A is 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? And then I got to figure out what z is. So let's see. If if B is 0, I don't know if I have to even look at the state machine. I could just say B is 0. I'm just looking at the AND of these, right? So 0 and 0. I'll skip to the third row. 0 and 1. Let me put lines here. 1, 2, 3, 4. Yeah. OK. So yeah. So B is 0. So it's 0 and 1. So that's a 0, 0, 1, right? And then if B is 1, it's an OR. So that would be 0 or 0. That would be 0 or 1, 1. That would be 1 or 0, 1, 1 or 1, 1. Right. So there's the output logic. And again, it's a Mealy machine, so the output logic is current state and inputs. Right? If this were a Moore machine, I would not be allowed to put A and B inside this table if this were a Moore machine. OK. Is that it? I think that's it. Oh, and there's a timing diagram, too, on there somewhere. Let's see. Yeah. And then as far as the state that this goes, I mentioned that the current state in this case is like a delayed form of A. So notice what they did here. They actually, in order to make this more clear, notice how A changes a little bit off from the rising edge of the clock. So in that sense, your current state is going to transition. Well, we don't know what it is initially. Well, actually, we don't. We don't know what it is until this first rising edge. But after this rising edge of the clock, we know that the current state is going to be a 0, because that's what A is shown to be 0 before that first rising edge. This rising edge is still going to see an A of 0, so the current state will be 0. This rising edge sees an A of 1, so the current state will be 1 in this cycle. You guys with me? And so basically, what's happening is if you were to plot the current state, it would look just like A, except it would be shifted to the right by 1 cycle. Yes?
So in the second frame, is that current state 0 and the next state 1?
Yeah, the next state would be the next state would be 1 whenever A. So the next state would be A in this case, right? The next state and A are the same in this case. So the current state is just A. So the current state would be the same as A, and then the next state would be would look the same as well, except it would be shifted, right? So we wouldn't go into the next state 1 until this cycle, right? Which is 1. It's like this shifted this way, right? Right. So you could build the next state by just taking A, copying it, and then sliding it to the right by 1 cycle. Any questions? The schematic, by the way, I didn't show this. It asked for the schematic here. The schematic, you'd have to build the schematic from the, you could do a K-map of this table and then build your schematic from there using the stuff from chapter 2. OK. So last time we also talked about timing a little bit. So registers and flip-flops have these timing constraints called setup and hold time, meaning that you have to ensure, when I say you, I mean usually what I'm talking about is the tools that generate the hardware. Generally speaking, the way this works is, like you're probably already thinking, like at this point, once you start introducing rules about setup and hold time, this is already a little bit too complicated to incorporate into a hand-built design. Right? I mean, I guess you could with a simple thing like this, but generally speaking, what I'm talking about now are rules that have to be obeyed by a compiler, essentially a synthesizer that takes hardware description code, which is we're going to cover in the next chapter, converts that to logic, and the logic that it generates, the sequential logic that it generates, has to obey these timing rules. And the timing rules is that whenever you have a flip-flop or a register, the input to that, the D, the input, has to be stabilized by whatever by the time of the clock edge minus the setup time. That sounds kind of strange, but it has to be stabilized. It has to be stable for T setup prior to the clock edge. Okay? And it has to be also stable for T hold after the clock edge. Now together, these two values are referred to as the aperture, meaning that the aperture is kind of like from, it's how long, it's the window of time where the register of the flip-flop has to see a stable input. If it doesn't, it still works, but it goes into a state called metastability, which we'll talk about in a minute. But as long as you don't change the input inside of this period of time, this aperture, then the register will behave in a predictable way, and it will update its Q according to the propagation and contamination delays associated with the register of the flip-flop. You guys with me? Does it make sense? In other words, it'll act predictable. It'll be predictable as long as you don't break this rule. If you break this rule somehow, sometimes it's unavoidable, which I'll get to in a minute. If you do break this rule and you change D after the setup time and before the clock edge, or after the clock edge but before the hold time elapses, then it behaves a little unpredictably, right? And of course can cause your circuit to behave unpredictably, which is a fault, it's a problem, it's a bug, right? You guys with me? Okay. So how do we the question is, how do you guarantee that? How do you know? How do you know that D is not going to change within the aperture time? Well, the flip-flops, the standard cell library you get from the whatever like when you're doing if you're taping out a chip, you want to fabricate a chip, you'll get a standard cell library, which is a library of primitives like gates and flip-flops, right? They will be characterized, and the characterization data will include the contamination and the propagation delay of the flip-flop. I used to teach, we used to have a class here, 613, in which we would actually run a tool called Signal Storm. Was that Cadence? Cadence Signal Storm. We had a tool called Signal Storm that would actually take your library and it would figure all this out for you. Like you would design your flip-flop and then you pass it into Signal Storm, and Signal Storm actually figures out through simulation, it actually does simulations, it internally does simulations, analog simulations, SPICE simulations. But it figures out what these values are, and then it saves it as part of your standard cell library, which then has to be given to your synthesis tool when you're actually generating your logic circuits. Does that make sense? It's kind of complicated. We don't have to worry about it here, but just that's kind of how this stuff works in practice. Okay, so contamination delay means the same thing as it meant in the last chapter. It's the minimal amount of time before an output could change, in this case after the clock edge, because normally when you talk about contamination delay with logic gates, it's if you change the input of a logic gate, how fast will that logic gate output start to change, and then the propagation delay determines how long it takes to stabilize, or how long it takes to reach its final value. You got, right? But with when you have the contamination propagation delay with respect to a flip-flop, it's in reference to the clock. You know, how long after the clock edge do you see a change in the output, and how long before it stabilizes? So that's the contamination and the propagation delay. So when it comes to guaranteeing setup time, we consider propagation delay, because setup time is the time before the clock edge. So we're looking for the worst case amount of time it'll take for whatever logic is driving my D input to stabilize, right? So setup time is concerned with propagation delay. Hold time is concerned with contamination delay, because the idea with hold is that once the clock edge happens, it's game on. We got to do the next amount of work for the next cycle, but we have to hold the inputs. We don't want any inputs arriving at D before I'm ready for them, right? And that's the hold time. So the hold time has to do with, is a function of contamination delay, right? Does that make sense? So setup time, think of it this way. Setup time is what's going on in this cycle. Hold time is about worrying about what happens next cycle, right? Okay, so here's a typical data path, and this is the data path that makes up a CPU. I mean, a CPU is literally nothing but a collection of these data paths. You've got some sort of memory that's connected to logic that's fed into another memory, and these data path operations are what execute individual instructions within a CPU. So you have a clock edge, which in the notation here is TC, clock period, I should say. TC, clock period, that's 1 over the frequency. So if this is a gigahertz processor, then my TC is 1 nanosecond, right? Right? Gigahertz is 1 billion cycles per second. 1 divided by 1 billion is 1 nanosecond. Right? So TC is the clock period. It's how long is the clock cycle. The clock cycle has a falling edge in the middle, but who cares? Nothing cares about that unless we're doing something on the falling edge and the rising edge. But generally speaking, on the chip, you don't. Memory does this. That's what DDR memory does that. But internally on the chip, you generally have the clock set up to where you have the clock set up such that the time from rising edge to rising edge is minimized, right? So we don't care about that falling edge. Don't let that confuse you. You ignore the falling edge. You just look rising edge to rising edge. So within that cycle, rising edge to rising edge, you have to add up the propagation delay of that guy, right, of the memory that's feeding the data path, the combinational logic, to that, and make sure that gets done before the setup time for this guy, the destination memory. Okay, so that's shown, let's see, yeah, here we go. So if you look at TC, TC must be greater than or equal to. Now, a lot of times, for a lot of data paths, the TC is big, plenty big enough, right? But remember that propagation delay is always about worst case, worst possible delay through a circuit. So you have to bound this according to your worst possible delay. So it's got to be greater than or equal to the propagation delay of the registers that are feeding this, which these registers are generally all the same register. So it's, T, P, C, Q is associated with whatever register you're using, plus the propagation delay of the logic. Now remember, with the logic, you have to find the critical path. So this is the worst case propagation delay. So you have to add up the propagation delay of all of the logic gates connected in here serially, right, along the longest delay path. You guys with me? So you got to trace every path through here. And then you have to add the setup time for this, because that's the extra margin you need. You have to, this propagation delay at this point has to arrive before the setup time. And then you can rewrite this the same way as the propagation delay must be less than or equal to the clock cycle minus the propagation delay in the setup. Now you might say, why is it rewritten this way? I mean, what's the point? Why is this form emphasized? It's because you can't really control you can't really control this term, and you can't really control this term. These are kind of locked in. And so there's really only 2 degrees of freedom for the designer. There's the clock speed, which generally speaking, you try to pick that early on. And then once you pick that, now you've got TPD, and if this is too big, if this value is too large, you can change that. You can go in and you can try to change the critical path here. How do you do that? Oh, use the Boolean theorems. You can change the logic. You can make trade-offs. You might be able to do something in here that gives you the same logic value with a different propagation delay. You guys remember that, right? I talked about why do we have those Boolean theorems? Because you can use the Boolean theorems to make transformations in here that can give you the same Boolean function, the same sort of truth table, the same behavior, but you can have, like maybe a shorter path. You guys with me? Right?
So in the logic up there, could we also use that to find the TPCQ and T-setup?
No, these are locked in, so you can't change those. Those are TPCQ and T-setup are something that you cannot control. Those come to you. Those are basically a function of the technology, right? So for example, like this is, by the way, you know how like you've got Moore's law, and Moore's law makes the fabrication technology better with every generation. These are some of the terms that shrink with Moore's law, right? So if I want these to be better, I got to go and just wait a generation. I got to wait for the next generation of Moore's law. But until then, I can't do anything about those. These are linked to the semiconductor technology that you're building your circuit on.
All right.
Okay, and then the hold time constraint is, as I was saying earlier, the hold time is really about contamination delay. So we want to make sure that the hold time is less than the contamination of the register. Now, here's the idea here. Like, so when the cycle comes, like at the beginning, like right at the rising edge of the everything is fine. Everything is nice and calm right here at the input, right? Because of the setup time, right? So there's no activity here. But once that rising edge comes, 2 things are going to happen. The first is this guy is going to activate, changing the inputs to the combinational logic. So the minimal time before you see activity at the input to this register is the contamination delay of this register plus the contamination delay of the logic, right? Contamination delay, again, that means the minimal amount of time before something happens, before something changes. So whatever the contamination delay of this is plus this, right, must be greater than, it must be slow enough that by the time that contamination propagates through here, the whole time of this guy is over, right? That's why the whole time has to be less than the contamination delay of everything that precedes this register, right? Which, the source register plus the logic after it. Make sense? And again, they rewrite the equation to say contamination delay must be greater than these 2, because this is something you can change. And in fact, you can change the contamination delay easily. Easy. Just add buffers, right? You have these things called buffers, which are gates that don't do anything. They're like dummies. Like whatever the input is just the output. So you can add buffers in there if you want to change the contamination delay, right? Easy. It's going to cost you transistors to do that, but it's not hard to. That's an easy thing to change. But you still have to make sure that holds. Okay, so here's an example problem. I'll definitely ask you something just like this on the exam. The timing characteristics, there's a circuit. This circuit is a little different from what I just showed you because this is an actual circuit. This actually shows the source registers and the destination registers. And in this case, you see a more realistic, instead of just a box that says CL, it's actual combination of logic. And so in this case, it gives you the contamination and propagation delay for the registers, which is 30 and 50 picoseconds. How do I know that's the registers? Because it's got 3 letters here, C, CQ, and PCQ, right? Also, the gate contamination and propagation delays are given PD and CD, and those are for gates, and I know that because there's 2 letters here, subscripted letters, right? The subscript is 3 letters here and 2 letters here. Okay, so I've got the setup and hold time here as well. right, for the registers. So the question is, does this work? Is this going to work out? Is this circuit going to work, or is this circuit not going to work? Well, to figure that out, we got to figure out the total contamination and propagation delay for the logic. The logic's contamination delay is going to be based on this path right here. This D goes through only one gate. And so the contamination delay for this whole block of logic is going to be this one gate's worth, just because we have a path that only has to go through one gate. So that's going to be 25 picoseconds for the logic. So 25 picoseconds for logic. The propagation delay is going to be the one starting from A or B, because A and B have to go through 1, 2, 3 gates. So the propagation delay is 35 picoseconds, and I have to multiply that by 3 because my longest path goes through 3 gates. So my propagation delay is 3 times 35, which is 105 picoseconds, right? All right, so that's all I need to know to do the analysis. So the question is, for setup time, I need to know if my setup time, oh, I need my clock speed too. What's my clock speed? Oh no, I don't know the clock speed. I'm trying to find, sorry. In this question, I want to find the max clock speed. If they had given me the clock speed, I would be asking if this circuit is going to work or not, right? But initially, for setup time, I want to find out what my max clock speed is. And then once I figure that out, then I can figure out if I violate my setup time, my hold time constraint. You guys with me? Right? So I don't know the clock speed yet, but I'm going to figure it out. I'm going to figure it out because my clock period has to be long enough to allow for the propagation of the registers, which is 50, plus the propagation of the logic, which is 105, so that's 155, plus the setup time for these guys, which is 60. So it's going to be 50 plus 105 plus, oh, here it is, plus 50 plus 105 plus 60 has to be at least 215 picoseconds. So that's 215 times 10 to the negative 12th power. And then you take the inverse of that and you get 4.65 billion, 4.65 gigahertz, right? So once you find the period, then you can find the frequency by just taking the inverse. Make sense? Okay, so now this is the fastest I can run this circuit. Now you still have to check the contamination delay, though. The hold time, which is based on the contamination. The hold time says that I have to make sure that I hold for 70, right? So I need to figure out, is this input going to hold for 70? Well, I don't know. The contamination delay is 30, so this D is going to change in 30 potentially. And this gate is going to change in 25. Right? So 30 plus 25 is 55. Right? So this gate, if I change D, if I bring a new D into this register, that new D may propagate through here in 55 picoseconds, which is too fast. The hold time is 70. It's too fast. That'll violate my hold time. Right? So in order to fix that, as I mentioned earlier, you can add dummy gates here to increase the contamination delay. Right? And so if you add the dummy gates, what does that do? Well, each dummy gate is going to add another 25. So this is 25 and 25. That's 50, no problem, because the whole time is, it would be 50 in total plus that, which is 30. That gives you 80. Same thing with this path, too. You guys with me? So by adding that buffer, it changes my contamination time to 80 if I did my, 80. 30 plus 50. Any questions? Okay. Okay, but there's another added complication to all this, if that wasn't tough enough. There's also this notion of clock skew. So any chip is going to have lots and lots of flip-flops and registers all over the place, and RAMs, distributed across the whole chip, and they're all connected by a giant clock network. Right? The clock network is problematic because it's so big and connects to so many things that it's made of a lot of metal, meaning that it has a lot of capacitance, meaning that the clock network is going to be hard to maintain the clock speed you want because you got to drive a lot of capacitance. But also there's this clock skew because if you look at what the clock at various points on the chip, they may not be synchronized. Your clock edges may not be synchronized at different points on the chip. You guys with me? Like when you the clock comes into your chip, connects to the clock network, and the farther away you get from that connection point, the pin, the more lagged the clock may be. You guys with me? So that's what clock skew is. Clock skew is the maximum difference between the clock edges at different points of the chip. So what that means in terms of the timing analysis is that you have to consider clock skew because if you have your source register and your destination register, they may not have the same clock. They may be skewed. Meaning, in the worst case, now you don't know how they're going to be skewed relative to one another, but in the worst possible scenario, which you have to account for, this destination register may have a clock edge that is actually coming before clock 1's, the source register. Right? It's possible. Depends on where the clock is coming into the chip. Where is the clock source? Right? The way that you place these registers on the chip may put this register's closer to the clock source, meaning that his edge may become before this guy's edge. So if that happens, you have to add the skew when you calculate the propagation time. Right? And thus, when you're doing your setup time calculations. So this is the same things that we have the skew. Skew, again, the skew is the worst, the highest possible difference between two clock edges on the same chip. That's the skew. Now, by the way, this is kind of a gamble you play, right? In fact, I do this all the time. Like, I'll do a design on an FPGA, and you run the timing analysis, and the tools will say, oh, this design should run at 200 megahertz. And I'm always like, I'm going to run it at 225 and see if it works. Right? Because the timing analysis tools, it turns out actually it's even more complicated than this. Not only do you have to consider skew, but you have to also consider temperature variations of the chip. So when you do timing analysis, it considers the worst case propagation delay, it considers the worst case skew, and it considers the worst, it runs it as if you were running, it considers the behavior of the circuits at 100 degrees Celsius as well, which everything slows down at that temperature, at higher temperatures. So it considers the worst case. So when the tools say, oh, it's 200 megahertz, it guarantees it'll work at 200 megahertz even in an oven. But that doesn't mean you can't overclock a little bit and have it still work. Now, how much can you overclock it? Unclear. Also, aging effects. I forgot about that too. These circuits also age, and they get slower with age. So there's age as well. Age is caused by electromigration, which is the degradation of the substrate of the chip. So the tools consider all those things. So as a user, you're like, yeah, I can always add a little bit more to this. Tools say 200 megahertz. I can probably run it 225, maybe 250. But you're taking a risk. Okay, and then with hold time constraint, in this case, you have to consider the skew here as well. In this case, you have to make sure that you have to add the skew to the hold component. So it's kind of the reverse, where you may have to hold it longer because the edge of the destination register may be coming before the source register. Sorry, no, actually it's the opposite. It may be coming after, right? In this case, this guy's edge may be stretched out a little bit longer, right? Which means that I got to hold for longer. Because this destination guy may be thinking that he's receiving the clock edge later. And so you have to add the skew to the hold time. Does that make sense? So you have to think of it kind of in reverse. Because with the skew, it could go either way. This edge may be before this guy or after, depending on where you place these on your chip. Any questions about that? OK, so that's timing analysis. Now, this is what about, so if you're laying out data paths, the tools can guarantee that the setup and hold time constraints are not violated. Because why? Because they're generating the circuits. But what about if there's something you can't control, like, say, an input device? Now, how does this work? Like, if you have a circuit with a button, you have a user hit a button. Now, generally speaking, you're going to capture that button press with a register, with a flip-flop. You're going to have the button connected as the D input on a flip-flop. So the user is going to hit a button. You're going to capture that every clock edge, right? Right? We do that in 613. We do it in 313. Sorry, 313, the embedded systems class. We take buttons and connect them directly to registers. We don't even think about it. But wait, when you think about that, though, wait a second. I mean, if the user hits a button, and that button is connected to D, and we're sampling that D on a clock edge, what's to say that that user won't hit that button inside the aperture time? Nothing. And there's no way to guarantee that the user won't hit the button inside the aperture time. Right? It could be a user hitting the button. It could be a sensor. It could be an asynchronous SPI channel from another chip. It doesn't have to be a button. You know, buttons are slow because they rely on a human hitting it. But it could be a digital signal coming from outside the chip. Any digital signal coming from the outside the chip cannot be guaranteed to be outside, to change outside the aperture, right? So what do we do about this? Well, it turns out there's nothing you can do. You have to take the risk that any digital signal coming from outside your chip can possibly change inside the aperture. And if that happens, your register will become metastable. You guys with me on this? Metastable means that the flip-flop will capture the value as something between 0 and 1. Right? Now, the thing about that is it doesn't stay like that forever. Because things aren't perfect. So even if you capture a half of a 1, you capture like a half instead of a 1 or 0. You capture some voltage inside your feedback network, inside your latch. You capture that, and it stays in this weird quasi-state that's in the forbidden zone between 1 and 0 for a while. But eventually, it'll stabilize. The problem is that you don't know how long it's going to take to stabilize. It depends on several factors, one of which is where inside the aperture did the user hit that button? At the beginning, at the end, or in the middle somewhere, right? Also, it depends on the technology. It depends on what the propagation delay is of the gates, and it depends on the gain of the transistors that make up the gates inside the latch, right? So there's a couple different parameters. There's two main factors that you have to consider. One is when did it happen inside the aperture, and two is what is the internal characteristics of the circuit, right? But suffice it to say, it's not going to happen inside the propagation delay that you get from Artisan or whatever the company is that supplied your gate library, your cell library. So we have this weird, sort of uncertainty, right? Yeah. So here's the cross-coupled RS latch that we looked at the beginning of the semester. Here's your cross coupling. And the problem is, yeah, if you go into a metastable state, you end up with a Q in here that's like between 0 and 1. And it'll stay that way for some amount of time before it eventually goes to either 0 or 1, right? So the book has this, this equation that says it's the probability that the resolution time, which is the time it takes to resolve, to actually stabilize the output, is greater than some value t that you give it, that you're proposing, is equal to t sub 0 divided by tc. This component forms, now t sub 0 is a parameter you get from the technology. It's locked in. Tc is the clock period. And this parameter, this t sub 0 over tc, is the component of this that determines where the change happened within the aperture. Does it make sense? So what do we know? We know it's metastable. How did it get metastable? The d change in the aperture. This determined where inside that aperture it changed, right? So this is kind of a parameter that determines that. And then you just have a exponential, e raised to the minus t divided by tau. Tau is just another parameter you get from the technology. You guys with me? So this just forms an exponential distribution that says that if you look at the time, so what it means is that the more time you wait, the more likely it is that the latch will come out of the metastable state. So at time 0, this is 1, and it just does one of these numbers, right? It looks like an exponential distribution. The shape of this curve, though, is going to be determined by that tau, right? Right. So the longer you wait, the more likely it is you'll get out of the metastable state. But it's based on this probability distribution, which is basically just an exponential. Okay, so what's the point of knowing that? Well, the point is that we can create something called a synchronizer. A synchronizer is an approach you take to try to solve the problem of inputs going into this metastable state. But it turns out that a synchronizer is just you just take two flip-flops and put them and connect them in series. So you've got like the button here, like the D is the main input coming in from off chip. It goes into one flip-flop, which may be metastable, but then its output just connects into another flip-flop. Now, what's the point of this? The point is that by doing this, by creating a synchronizer this way, we can come up with we get an idea based on the propagation delay of this. We can get an idea of how likely it is, or how often that this Q will be metastable. Does that make sense? See, like if you just have one flip-flop, it's entirely uncertain, but we can characterize this this circuit. So the idea is that if you get a clock edge and this D2, which is the output, this internal signal, if that becomes metastable, it's okay, as long as it comes out of being metastable by the time of the setup time for this guy, for F2, right? So this guy is metastable for this amount of time. As long as it comes out, which it is likely to do, by the time before the setup time minus the next clock edge, then this guy will not be metastable, right? So we're essentially sacrificing this flip-flop and hoping to get a clean signal on this second flip-flop. So this way we can calculate a probability of failure by setting our t value, the t value, to be tc minus the setup time. So we can lock in this term right here, which previously was just t, and we can lock this in to be these two values, tc, which is our clock speed that we know, and t setup is known from our flip-flop. We can substitute these in for t, and this gives us the probability that we'll get a failure at q. And then we can come up with the probability of failure per second if we know how many times we're planning on changing this input. So now we're going back and saying, all right, we've got this synchronizer. We're going to use it to clean up this D input. But how often is the D input going to change? Well, if it's just a button that a user presses, probably not very often, right? But if it's a signal coming from another chip, it might be changing quite a bit. So there's this other term n, which is the number of times we expect the overall input to change per second. So if we have n is the number of times our input's going to change per second, the frequency of the input signal. And we have tc, which is our clock frequency, and t setup, which comes from our spec sheet for our flip-flops. We can then calculate the failures per second, and then if you take the inverse of that, you get the mean time between failures, right? Right? So the idea is that this, even if n is fairly large, this value may be pretty small, right? This may be 1 over 10,000, right? So if you take the inverse of this, you get the mean time, 10,000 seconds, for instance, between failures that you expect. Everyone with me? OK, so here's an example of that. So here we have a synchronizer. We've got a 500 megahertz clock, meaning that our TC is 2 nanoseconds. We've got our T0, 150 picoseconds. Where'd that come from? That's just a function of the technology. That comes from the fab. Tau is 200 picoseconds. Actually, it comes from the fab and the standard cell library. But these T0 and tau are just parameters that are always given to you. Notice they're in seconds. Units are seconds for both. T setup also comes from our. It's a parameter that's locked in. It's part of our flip-flop spec. And then n is the input. So this D is going to change 10 times per second. So what is the probability of failure, and what is the mean time between failures? So it's simple. You just plug all these into the equation. In this case, the probability of failure is 5.6 times 10 to the negative 6, which means you take the reciprocal of that, and you get 5 hours. Make sense?
So for synchronizers,
Yes.
Why don't you consider the hold time constraint?
Well, you can't, because the time constraint, the timing constraints are for the synthesizer, the thing that generates the circuits, right? You basically it's normally a time constraint is about how much can you pack into a data path, right? And people obviously want to put more in the data path because in the terms like in a CPU, the more stuff you can pack in the data path, the less number of cycles you need to perform something, right? So that would translate into a better cycles per instruction, for instance, right? If you have to start taking logic out because you're violating timing constraints, then you may have to add more cycles, which will cause you to do more cycles per instruction, right? It'll cause the performance to lower, right? So everyone wants to put as much work into one cycle as they can. In the case of a synchronizer, that's when you can't control it. That's only for external stimuli, stuff from coming outside the chip, like an input device or something like that. So in that case, the best you can do is put a synchronizer in and hope that that we can get a clean signal from it.
What I was saying was if the first if D2 goes into metastability and that metastable value reaches F2 within F2's hold time, then couldn't that cause Q to go into metastability?
Yes.
Okay. So but you don't worry about that possibility?
Oh, I'm sorry. I see what you're saying. You're worried about the path, the contamination delay of this path. I see. I'm sorry. Yeah. That's a good point. I guess the assumption here is it's not stated, but you could just put a bunch of buffers here or something to avoid that problem. Yeah. But that's a good point. The contamination delay here would be very short, obviously, because there's nothing shown here. But that's a good question. Yeah. Okay. All right. Great. Well, this is working out well. Any questions so far? Might have went through that a little too fast because I didn't expect to get this far. So this is the last topic of chapter 2 is parallelism. So there's 2 types of parallelism hereabout, and this is, by the way, we're talking about hardware parallelism. We want to be able to. This is kind of an odd thing to introduce here, but it's important. This is kind of one level up now. The idea with this is that we're going to start designing circuits. We're going to go one layer of abstraction up and start building actual functional units, things that do work in the hardware. And there's different ways to organize functional units that you build into your hardware. So there's a couple terms. There is this idea of a token, which is a group of inputs that will come into your circuit and will get processed and eventually produce an output. So you can think of this like let's say you're building a floating point unit, and you have 2 inputs come in and you want to add them. You have 2 floating point inputs come in, and generally speaking, a floating point operation takes multiple cycles. So you could think of those inputs sort of propagating their way through a circuit. And generally speaking, at this level, you're talking about clock cycles. How many clock cycles is it going to take to perform that operation? And then there's latency is the time it takes for one token to pass through your logic from beginning to end. And there's also throughput, which is the number of tokens produced per unit time. So it's how many how much work can you get done per unit time, essentially. So here's an example. This is kind of usually these, it's kind of a strange example because normally, like in the Hennessy and Patterson book, they have an example. The most famous one is doing laundry, because there's this multi-step process where you have to wash your clothes, you have to dry your clothes, then you have to fold your clothes, and then you have to put them back. So you have this kind of pipeline, multiple stages you have to bring your clothes through from the time you start washing them to the time they're put away and done. In this case, they have this cookies example where they say Ben BitDiddle bakes cookies to celebrate the traffic light controller installation. It's a callback to the example earlier. It takes 5 minutes to roll cookies and 15 minutes to bake. So you roll and then you bake. What is the latency and throughput without any kind of parallelism? So the latency would be the 5 minutes to roll plus the 15 minutes to bake, right? So 20 minutes. And the throughput is going to be 1 batch of cookies for every 20 minutes, right? Right? Yeah, so 3 trays per hour is the throughput, 1 every 20 minutes. And the latency is 1/3 an hour. Now, I mentioned there's these 2 types of parallelism, spatial parallelism and temporal parallelism. Spatial is if you have someone else doing the same thing in parallel, right? So that way you can take 2 batches of cookies and have 2 people trying to, bake them and roll them and bake them at the same time. But then there's also temporal parallelism where you can have 2 people, 1 person rolling and 1 person baking at the same time. That way you can have 2 batches in the pipeline, right, at one time. Does that make sense? So if you're just using spatial parallelism, you can have two trays going on at one time, but the key here is that you start them at the same time. So you have two people, one person per tray, and so in this case, your latency is the amount of time it takes to get one tray through. It's the same as it was before. It's going to be 20 minutes. The only thing that changes here is your throughput, because now you can get two trays every 20 minutes, right? So that increases your throughput, but does not affect your latency. On the other hand, what if you used temporal parallelism? You can have once you get done, you can have one person that just does rolling. So you roll the first one, then you roll the second one. You can have another person that just does the baking. That way you overlap the rolling and the baking, right? So tray 1 starts at time 0. Tray 2 starts at time 5 because it's 5 minutes to do the rolling. And then the baking, part of the baking process would happen at the same time as the rolling process. The problem is that they don't both take the same amount of time. So you're still going to have some time where the roller doesn't have anything to do, where you lose utilization. So in this case, your latency, once again, doesn't change, but your throughput does change, because now you can get one tray in every fourth of an hour. How does that work? Throughput. So in this case, so the idea is that you get one tray in every fourth. How does that work out? Because you're getting two trays done, one tray in every 4. How do they calculate that? You get two trays. Tray 2 finishes here. Yeah, so you got two trays done in 35 minutes, right? So that doesn't come out to be.
I guess after you've done one, that's 15 for every successive one.
Right. Yeah. Right. Once you fill the pipeline, that's right. So you're just looking at, you're looking at the difference between, that's a good point. Yeah, if you look at the difference, you get one done at 20, one done at 35, and then one done at 50, right? Yeah, the problem is that in this case you have to fill the pipeline. So the first one won't come out till 20, and then subsequent ones will come out every 15 minutes after that. All right. So that's the last topic.